Hello students, Mr. Courtney here. In this video we'll be talking about chemical equations and more specifically the type of reactions. Our objectives will be to interpret symbols in chemical equations, predict the products of chemical reactions, identify the types of reactions, and write and balance chemical equations. Here are some of the symbols that you will see in chemical equations. So we have solid, gas, liquid, aqueous, meaning dissolved in water, and we have reactions that are reversible. That means our reactants produce products, and these products can also react to give us the reactants back. So the reaction can go in the forward direction from reactants to products or from products to reactants. A catalyst is something that speeds up a chemical reaction, and the catalyst remains unchanged at the end of the chemical reaction. So in this case, platinum is required for this reaction to occur, or it speeds up that reaction. But in the end, platinum, which is a catalyst here, will not be changed. Then we have either heat is added. We have this one here with a delta sign, a triangle, tell us heat is added, or we can simply put the word heat at the top of the arrow. So let's start with the first type of reaction, decomposition. Decomposition meaning to break down. So we have one reactant breaking down, or one reactant forms two or more products. So we start with one substance. We start with this substance here, and that substance breaks down to give us two new substances. So we have our one reactant breaking down to give us two new products. And that requires energy. So energy is required in the form of heat, light, or mechanical shock. So that means we must add energy into this part, into our reactant side for this to occur. Synthesis, meaning to make. So we start with two reactants, we form one product. So we start with two separate substances, and these two separate substances combine to give us a new substance. Now, when we have our transition metals, and these transition metals have multiple oxidation number, and oxidation number is the same thing as their charge. They can have multiple charge. So for these elements here, whenever they form compounds, we're going to use their higher oxidation state or the higher charge. So as stand fell, huge cups crack. Okay, so these elements here we're always going to use their higher oxidation numbers. Now for these cobalt, nickel, manganese, lead, antimony, bismuth, we're going to use the lower charge. And we'll see some examples of that as we go along. Singular replacement. Replacement meaning to take the place off, to put in place of. Single meaning one. So what we're seeing here is that one substance wants to take the place of another. So a more reactive element takes the place of a less reactive element in a compound. So the less reactive element has to be in a compound, and the more reactive element is going to be free, and it's trying to take the place of that element, that less reactive element in a compound. So here we have a compound between A and B, and C is that element that is trying to take the place of B. The only way C can replace B is that C has to be more reactive than B. How can we tell if it's more reactive than B? We look at what is called the activity series, and the activity series will help us determine if that reaction will occur. This is what your activity series would look like for your metals. So here we see that nickel is higher than copper in the activity series because our activity increases from bottom to top. So that means, let's say cobalt can replace copper, but copper, which is lower, cannot replace cobalt. Now you may be wondering, if we were talking about metals, why is hydrogen here? Remember, hydrogen behaves like a metal and a non-metal. Even though it's a non-metal, it can gain electrons, it can lose electrons, so it behaves like a metal also. So again, an element can only replace one that is lower than it in the reactivity series or your activity series. So calcium can replace any of these elements that are below it, but none of these elements below calcium can replace calcium in a compound. All right, so that's just basically what we said here. An element can only replace one that is below it on the activity series. Now, the very reactive metals of group 1A and 2A, they react with water to produce hydrogen and a metal hydroxide. So we have sodium. Sodium reacts with water to give us our metal hydroxide and hydrogen gas. So here we see sodium is a solid, water a liquid. Sodium hydroxide will dissolve in water, so it is aqueous. Hydrogen is produced as a gas, H2, so that's why it's shown as a gas. And just to help us, if we're going to be using any of these transition metals here, or these metals, acetylene, tin, iron, mercury, copper, chromium, we're always going to use their higher charge. So here we see for iron reacting with copper sulfate, or copper 2 sulfate, iron can replace copper 2 sulfate, and it does. So how do we know which charge to use? Let's think about it. Remember, sulfate has a -2 charge. -2 times 3 is -6. When we form compounds, the positive charges must balance our negative charges. So if we have an overall charge of -6, that means our overall charge must be, our positive charge must be 6 also, +6. So we divide +6 by 2, that gives us +3. So we see we've used our higher charge for iron in this case, which is +3. And a reminder to use the lower charge for these elements. Now a double replacement reaction. The cations in two compounds switch places. So the positively charged species are going to switch places. A neutralization reaction is an example of this. Because we have our cations here, hydrogen is our cation and potassium is our cation here. And these two would switch places, as we see here now. So we have potassium chloride and water. So the hydrogen and potassium have switched places. A neutralization reaction is an example of a double replacement, and it's a specific one that we call an acid-base neutralization, where an acid, HCl here is our acid, reacts with the base to give us the salt and water. So salt, not table salt. Table salt is sodium chloride. Salt is a general class of compounds. Okay, so we have acid plus the base to give us a salt and water. That is a neutralization reaction, which is an example of our double displacement reaction. Combustion. A substance will react with oxygen, producing energy, and the energy is in the form of heat, and sometimes you can have light being produced. In most cases, you'll have light also being produced. When it involves hydrocarbons, remember these are the compounds that contain carbon and hydrogen, or carbon and hydrogen only. Sometimes you have other compounds mixed in with other elements like oxygen, nitrogen, sulfur mixed in with our carbon and hydrogen. The products here for our hydrocarbons, those that contain carbon and hydrogen, will always be carbon dioxide and water. And of course we'll have energy being produced. So now let's look at some examples of reactions. We're going to classify these reactions, write their balance equation. So we know this is a single replacement reaction because calcium, which is a free metal, is trying to take the place of magnesium. We look at our activity series. We find calcium, then we find magnesium. We see that calcium is higher than magnesium, so that means calcium can replace magnesium. So this tells us it's a single replacement reaction. So calcium will combine with the oxide to give us calcium oxide, and magnesium will be by itself. So our products will be calcium oxide and magnesium. We go ahead and write our equation, which is our skeleton equation. Then we have to ensure that the equation is balanced. We have one calcium, one calcium. one magnesium, one magnesium, one oxygen, one oxygen. So the skeleton equation is the same as our balanced equation. All right, copper 1 sulfide. Since we're starting with one substance, that means we're looking at a decomposition reaction. So copper 1 sulfide will break down or decompose into its elements. So we get copper and sulfur. We write our equation, copper 1 sulfide, copper and sulfur. You see that we have 2 copper atoms on the left side as a reactant and 1 copper. So we need as a product, so we need to balance that equation, and this will be our balanced equation. Zinc plus oxygen. So we classify this one as we have 2 substances being reacted with each other. So we classify this as a synthesis reaction. We get zinc oxide. We write the formulas for these compounds, zinc plus oxygen to give us zinc oxide. We see that we need to balance our oxygens. So we put a coefficient of 2 in front of zinc and a coefficient of 2 in front of zinc oxide also to give us our balanced equation. Aluminum phosphate plus nickel 2 sulfide. So we have 2 substances reacting. And here we'll see that these 2 substances, their cations will switch places. So we'll get nickel going with phosphate and aluminum going with sulfide. So that means this is a double replacement reaction. And sometimes you see it being called a double displacement reaction. So these are our products. We write the formulas for our reactants and products. You see that we need to balance off our nickel, our phosphate, our sulfur, and aluminum. All these need to be balanced out. So you can go through the process and balance this equation, and you will come up with this as your balanced equation. Sodium nitrate plus hydrogen. So hydrogen is the free substance here now, and sodium nitrate is our compound. So hydrogen is trying to take the place of sodium nitrate. So when you look at it, you find sodium on your activity series, and then you find hydrogen. Hydrogen is lower than sodium, so that means sodium cannot be replaced by hydrogen, or hydrogen cannot replace sodium. So that means this reaction does not occur. Propane plus oxygen. Propane is a hydrocarbon, C3H8. So that means we're looking at a combustion reaction. When we have combustion reactions with hydrocarbons, we know that we get carbon dioxide and water as our products. So we go ahead and write our equation. Propane reacts with oxygen to give us our carbon dioxide and water. Here we see that our carbons are not balanced, oxygens are not balanced, hydrogens are not balanced. So you have to look at it. How are you going to go about balancing this equation? You may want to start with trying to balance your hydrogens first. But if you put a coefficient of 4 here, that gives us 8 and 8. That gives us 4 and 2, 6. Then you need to balance off your carbon. So you'd put a coefficient of 3 here. So that gives us 10 oxygens in total. That means we need to put a coefficient of 5 in front of our oxygen gas. And that will be a balanced equation for this one. So in this reaction, we have sodium chloride plus fluorine. Now fluorine is a non-metal, sodium is a metal. So fluorine cannot try to replace sodium, or it cannot replace sodium, because metals can only replace metals. Non-metals can only replace non-metals. So that means the fluorine is trying to replace chlorine, or the chloride ion. Look at your periodic table, you see that fluorine is more reactive. Remember, it's more electronegative. It's also more reactive than chlorine. So fluorine is going to replace the chlorine. So that means we have a single replacement or a single displacement reaction. So we're going to get sodium fluoride and chlorine as our products. And you have to remember that fluorine, chlorine, they're all diatomic elements. So you have to remember you have 7 diatomic elements. I bring clay for our new house. So when you write the equations, fluorine will be a diatomic element. That's the way it exists in nature. Chlorine exists as Cl2. When they're in a compound, they're going to be just Cl or F in these cases. So we have our equation, our skeleton equation, sodium chloride plus fluorine gas or fluorine to give us our sodium fluoride and chlorine gas. But we realize our equation is not balanced because we have two chlorines, two chlorine atoms here, and we have one on the left. So we have to balance these off. Okay, so you go ahead and you balance off your equation, and this will be a balanced equation. So this takes us to the end of types of reactions. Until the next time, blessings. I'm out.